right, now that you've looked more closely at how covalent bonds form using the interactive, we are going to just take a few more notes about covalent bonds. So as a reminder, in a covalent bond, we are sharing electrons to fill the octet. And it always occurs between two non-metals. So if you have a metal, that's going to be ionic, if there's a metal and a non-metal. But if you have non-metals only, that's going to be a covalent bond. However, there are different degrees of covalent bonds. So I want us to look at the different types of covalent bonds. There are regular covalent bonds, also called nonpolar. And then there are polar covalent bonds. And then there are ionic bonds. So it's kind of a continuum. You could be over here and be close to being ionic, but still on the covalent side. And then you could be way over here and be like the most covalent bond ever. Okay, and then you could be over here and be the most ionic bond ever. So in general, your metals and nonmetals are going to fall in this range. And your nonmetals and nonmetals are going to fall in this range. But there's still what we call a continuum. All right? So polar covalent is going to be classified as anything that has an electronegativity difference of 0.5 to 1.9. So anything in this range, we're going to call that polar covalent. Greater than 1.9 difference is going to be ionic, and then less than 0.5 is going to be nonpolar covalent. Now, what do we mean by electronegativity difference? Well, in your textbook, on page 341, there is a list of electronegativity values for lots of different elements. And remember, electronegativity, let's make a note here. Electronegativity is the ability to attract electrons. So if two elements have a big electronegativity difference, like we see over here, a big electronegativity difference, then one of the elements is going to take the electron. So here we're taking the electron. Okay? If their difference is medium, which is what we see in this area, then they're going to share unequally. So they're sharing, but they're not sharing equally. Okay, one of the elements is going to kind of hog the electron, but it's not quite going to take it. Okay, sharing unequally is polar. And then under nonpolar, if they have very little difference, they are going to share equally. Okay, so label your chart here. If we have low difference, that's nonpolar, they share equally. If we have a medium difference, they're going to share unequally, that's polar. And if we have a big difference, one is actually taking the electron, and that is ionic. Right? So let's see an example of how we would figure this out. You need to refer to page 341 in your textbook. Alright, so if we have F and F, for example, fluorine bonded to fluorine. Fluorine has an electronegativity value of 4.0. And the other fluorine has an electronegativity value of 4.0. So 4.0 and 4.0, the difference between those is 0. So that's not polar. Those two fluorines share their electrons equally. However, hydrogen and fluorine, 2.1 for hydrogen, looking at that table, and 4.0, that's a difference of 1.9. So that falls in that polar covalent range. It's actually getting pretty close to being ionic. So here, they share unequally. And you see how this cloud represents the electrons, and it's kind of shifted over toward fluorine. You see it's darker and then lighter, if you can see that on your paper. It may not be as clear as it is on the screen. But what that's telling us is that the electrons spend most of their time around fluorine, because fluorine has a greater electronegativity. Now, what we want to get in the habit of doing is drawing an arrow to show where the electrons are hanging out. So in this bond, our arrow would go toward fluorine. And the tail of that arrow is going to have a plus sign, which means that this is the end that has less electrons, while the fluorine end is going to be more negative with the more electrons. All right, so that's polar covalent, sharing unequally. If we look at sodium and fluorine, sodium has a 0.9, and then fluorine has a 4.0. That's a difference of 3.1. So that is ionic. Fluorine actually took sodium's electron. So now fluorine is completely negative, and sodium is completely positive. All right, let's look at some other examples. Hydrogen and hydrogen. 2.1 and 2.1. So that's a difference of 0. So a difference of 0 gives us a nonpolar, completely covalent bond. All right, HBr, 2.1 and 2.8. That's a difference of 0.7. That 0.7 is greater than 0.5, so that falls into the polar covalent. They share, but they do not share equally. So we would draw an arrow toward bromine, because bromine is going to be the one hogging the electrons, and then a plus sign back here toward hydrogen. All right, here we have C and O bonded on each side. The electronegativity difference between those as 1, so that falls in the polar covalent range as well. And we'll draw our arrows. Now this time we have 2 bonds. So we would have an arrow on this bond. Oxygen is more electronegative, plus sign toward carbon here, and an arrow going this way toward this oxygen with a plus sign here. So we draw these arrows on each bond, okay? Carbon to oxygen and also carbon to oxygen. All right, lithium and fluorine, lithium 1.0, fluorine 4.0. That's a difference of 3.0. So therefore, that is ionic. Fluorine is actually going to take lithium's electron, so fluorine would be negative. No arrow. Fluorine is completely negative, and lithium completely positive in that ionic bond. All right, so to summarize, a molecule, which is a synonym for covalent compound, is 2 or more nonmetals that are bonded together. Those bonds, however, could be completely covalent, that would be nonpolar, or they could be polar in nature. And we're going to figure that out using those electronegativity values. Those are in your textbook. We'll subtract and see where they fall in the range. All right? So now that you've got that information, I want you to finish the worksheet for 4.1.